This is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the vibration measurement technique, which is the last module in that. And in the previous lecture, we discussed about the basics of the measurement techniques, because you see here, in any of the rotating machinery, we know that the measurement is one of the specific part, because prior to apply any control method, first of all we need to find out the configure rather the dynamic forces, and accordingly if we can find out that you see this is the basic cause, the root cause, we just want to treat, we just want to treat the root cause, and we just want to cure that. Straightway we can immediately attack on the root cause of these vibration generations. So, we know that you see these are the there are three the basic dynamic parameters like the displacement, velocity and acceleration, and all are representing their key we can say role in measurement of the forces straightway. And then you see here, even when we are going for higher frequency measurement, we know that the accelerometers are the perfect one, and when we are talking about the low frequency measurement well below the 10 hertz, certainly you see the displacement measurement is quite good enough for that. So, in the previous lecture we discussed entire things that how the accelerometer is basically working, and how we can get the accelerations means the inertial forces, and how we can configure that, especially when the vibrating masses are being there at the machine, right from the bearings to gears to any kind of the misalignment or the unbalanced rotor forces. Now, in this lecture you see here, we are trying to focus on the measurement technique from the data acquisition point. Means now you see whatever the data, whether it is in terms of the time domain or the frequency domain, how we can capture those datas. Even sometimes in the last lecture we discussed that you see here, this is really tough to locate the sensor at an accurate position, because when the things are being rotating, certainly we need to see that where we can keep the closest place, the close by area of the sensor, so that say if the bearing is rotating, shaft is rotating, gears are being under rotating motion, then what is the accurate location or some adjustable location, so that we can capture almost clear these the closest data which we are requiring. So, whether we are talking about the time domain or the frequency domain, we need to check it out that what exactly the data which are coming, and how we can just process that. So, in this there is a considerable variety of the extent and the method used to acquire and the log we can say vibration and the other diagnostic monitoring machinery parameters, because the methods and the corresponding products which are being available you see to accomplish the data acquisition tasks just constitute a constantly changing field, that is we can say just either parallel and perpendicular advancement in the PC and the workstations. Because you see here, when we are talking about the online fault or online vibration signature, we need to check it out that how we can process these data, how we can capture these data and process this data through that. So, data acquisition system, generally we are saying the DAC system, are used to acquire, to store and analyze the vibration data received from the sensor, and the sensing system utilizes the state of art computer based data acquisition system. So, the equipment is supposed to be optimized to sample at the rates commensurate with the highest frequency expected during the testing. So, that is one of the key feature, that what is the sampling rate is there to capture the data, and data may be acquired and submitted in different formats for further review and analysis according to the requirement of the analyzer. So, filtering may be performed during the acquisition, or we can say digitally we can say follow the data acquisition part. So, data analysis such as the Fourier transformation may be performed using various by various data acquisition system, in which you see the inbuilt these the transform functions are there. So, in general we can say the vibration sensor serves to detect the mechanical vibration and convert it into electrical voltage proportionally. and then you see whatever the like the conditions are there to fit the requirements requested by data acquisition system, the voltage may be amplified, filtered, or the other features are being there with that voltage. So, vibration sensor module can be divided into two main parts. First, the accelerometer sensor circuit, and second, the signal conditioning circuit. There are two first. One, whatever the sensor circuit is there based on the accelerometer or anything you see here, and second is what is the signal conditioning. How, whether we are just amplifying the signal, filtering the signal, we are like doing various other processes with the signal or what. So, the first item in any noise or vibration measuring is there is basically like just apply to the transducer feature. So, as you see, we are saying the transducer is nothing but the instrument which converts a signal into any from any physical form into another. So, this transducer, which in like we can say the sound pressure signal or vibration signal into the electrical signal. So, whatever the transducers are there which are being applied directly, they are just taking you see the like the pressure or any kind of you see the things, the mechanical system, we can say vibration signal, pressure signal or anything, and they are converting into the electrical signal. And this electric signal which is being obtained from the transducer, sometimes it is not directly we can see that oh what kind of like the signals are coming, we need to process that, we need to condition. So, some signal conditioner is being used to amplify, to attenuate you see here, or to transfer the signal using this A to D analog to digital converter. And it is you see like the optional at this stage to include the data storage system. Sometimes we are using, sometimes you see the signal processors are there directly, and through that you see here we can do. So, when we are going for the basic measurement part in this, we can see that this is what the signal which is the raw signal is coming to, like whatever you see the excitation feature is coming. So, it is being immediately you see acquired by the transducer. Now, you see this raw signal is straightway sending to the signal conditioner, and this signal conditioner, as I told you, is doing many of these such kind of applications. Then we can rather go for sometimes data storage, and sometimes you see it can be directly go to the signal processor, and through that the display display is there. This is a linear path which is being adopted right from raw signal to the display feature, in which you see the filtering, noise cancellation, various other things, the attenuations, various other things are being there right from raw signal to the final display feature. So, either way when we are talking about vibration signals or the sound signals, they are being produced by the transducers that are not normally in the suitable form of the study. So, first of all, as I told you that we need to go say that you see whatever the displacement or velocity or accelerations are coming, first the corresponding transducer or the sensor, like you see the displacement probe, velocity probe or accelerometer, is just capturing the things, it is sending to like the signal conditioning unit, and then you see here either the time domain or the frequency analysis, the frequency domain information is coming out. So, vibration analyst first begins with the acquiring an accurate time varying signal. As I told you, displacement, velocity or acceleration, a time varying signal from an like whatever the transducers are there, either from accelerometer, velocity probe or something, and the raw signal is typically brought into portable digital instrument feature, that is like that processes it for variety of user functions, and depending on the user's requirement for analysis, it is being now like absolutely the raw signal is being processed directly or routed to the mathematical integrators for conversion to other units of the vibration measurement. And depending on the frequency of the interest, the signal may be conditioned through various series of high pass or low pass filters. What basically our interest it just to see the high frequency ranges, though we are putting the low pass filters, where when we are interested to see the low frequency analysis, then high pass filters are being there. So, I mean to say that what exactly we are looking for, we are just looking the high pass. So, like it will pass through. When we are looking low pass, then it is the low pass frequencies are being going through. So, depending on the desired result, the signal may be sampled at the multiple times of the like and averaged out. If the time waveform analysis is desired, then like in the digital instrumentation, it is necessary to decide the number of samples and the sampling rate. So, the time period to be viewed is the sample period and times, you see, when we are just going like times to the number of samples, and most portable instrument, like you see, like we to incorporate the fast Fourier transformation processing, we are always see that what is the varying input sample and splitting into the individual frequency component, and then we are always making the continuous waveforms like that. So, basically vibration analysis is starting from the time varying real world signal from the transducer or the sensor, and from from input, the signal is absolutely going from various stages to filtered out or to like process this. And it is intended that you see here, we need to see that what exactly the internal processing path is there, through which we can simply see that like what the original waveform is coming out, and through that you see what is the detective frequencies are. So, when we are talking about the time like displacement or time velocity or time acceleration informations are, we need to convert into the frequency part, and as I told you, that can be done only by the Fourier this series. So, we are saying that the Fourier series and transformation is also one of the important tool to go like the entire signal, to take the entire signal into the fast Fourier transformation or the frequency domain. So, Fourier series decomposes the periodic function, and that is why one of the biggest drawback of the Fourier transformation, that if we have the non-stationary waveform in which the like the various parameters of the wave, the statistical parameters of the wave are being featured out. So, if like we are talking about the non-stationary form, the fast Fourier transformation is always giving the misleading information. So, this is the drawback, otherwise the Fourier transformation is the best one to see the detective, like the dedicated defective frequencies, or the like the frequencies which are being dedicated to the entire exciting zone. So, Fourier series, if you are going for the basics of that, the Fourier series decomposes the periodic functions or the periodic signals into sum of the set of simple oscillating functions. We can say like oscillating means the normal oscillating, the sinusoidal or the cos functions. So, you see here like when we are just going with the Fourier this series, we are saying that in the Fourier transformation, all this is the linear summation of these Fourier periodic signals. So, most machines emit the periodic disturbances to surrounding either in form of fluctuating forces which are being acting via the machine mounts, or in form of this sound which is also being like the simple harmonic motion. And the reason for these periodic disturbances can be like maybe we can say the meshing of gear teeth. In every rotation, when the problem is there in the meshing of gear teeth, they will again you see repeated themselves in every period. Imbalances in the rotating shaft, a periodic pressure fluctuation which is being arises in the cylinder of IC engine due to intake or we can say exhaust gases, and in every cycle you see here they will repeat that kind of you see the sound or the vibration in their motion. To analyze these problems in the frequency domain, a method is absolutely required which is to be divided up to the measured signal into the harmonic components, because that can be individually like done which can be individually analyzed and then linearly sum up that part. So, for periodic signal it is quite possible to use the Fourier series expansion, and then you see we can simply feature out the exciting frequencies that. So, this series, the Fourier series, is nothing but the expansion of the periodic function in terms of the infinite sum of sines and cosines, and you see like we can use the orthogonality relations like in making the relation between the sine cosine functions. So, the computation and the study of Fourier series for harmonic analysis is absolutely important, because through that we can break up the arbitrary periodic function into the set of various simple terms which can be plugged in and solved individually, and that can be recombined to obtain the solution of the original problem, or an appropriate we can say like accuracy can be adopted for checking out the clear filtration or clear excitation peak through this Fourier series solutions. So, when we are doing this, the first thing is the approximation of signal. So, the first step in deriving the method to decompose the periodic signal into the harmonic components, we need to first approximate a signal, like we can say that like a signal A of t with signal B of t. And when we are trying to fitting the two signals into just combining together, which is being there in say in the time period capital T, then we need to just see the approximation in simple possible way when we are multiplying sum of the constant just to adjust to see whatever the approximations are there. So, when we are trying to see this, the first thing is coming A of t, which is the main signal, is almost equal to B of t with the multiplication of that constant beta, and whatever the error is there in our approximation can be nothing but equals to A minus B of t into beta, that is what the error is. And we just want to average the square error which is being computed over the entire time period, this capital T. So, we can say the error now, which is the averaged square error, is nothing but equals to 1 for the total time period, 1 by total time into integration of 0 to capital T A of t minus B of beta into B of t whole square into dt. That is how you see we are calculating this, we are computing this error. And if you want to now minimize the error with respect to the coefficient beta, first of all we need to go with the minimum maximum part. So, minimizing this and putting this entire derivative equals to 0. So, d is this error divided by d beta, d epsilon by d beta is equals to 1 by t. Now, when we are differentiate it out this 0 to capital T 2 beta into b square t minus a of t b of t into dt equals to 0. So, we can say this constant which was intensely being there, it is nothing but equals to integration of 0 to capital T for entire time A of t into B of t into dt divided by this B square t into dt for entire time period integrations. So, now we can say that this concept which is simply showing the orthogonality there, if the signal A of t and B of t are orthogonal because of the sine and cosine part of this series entire, there is no connection between the two signals B and B equals to 0, the orthogonality condition for the two signal A of t and B of t for this time period, in this time periodical part in which you see the B this entire 0 to t A of t and B of t into dt is equals to 0 for making this property, we can say that the energy of the signal is absolutely proportional to the time integral of the entire signal squared. So, we can say E of A, which is nothing but the energy of the entire signal, is alpha times of 0 to t A square t into dt, where alpha is the constant you see which we are using. So, the signal which is composed of AT and BT, we can say that the energy is nothing but equals to alpha times of 0 to t AT plus BT whole square into dt, or we can say alpha times of integration 0 to t alpha square t dt plus alpha times of A square dt, or alpha times of 0 to t this B square dt into t, or else we can say that you see when we are expanding this plus alpha times of 0 to t 2A t and bt into dt. So, you see for the orthogonal feature when we are adding into the signal, we can say that the energy associated with the signal is nothing but equals to alpha times integration of t A square t into dt plus alpha times integration of t B square t into dt. So, we have the the energy associated with the individual term E A plus E B. So, when we are talking about the energy of the combined signal is the linear algebraic summation of the individual energy, and if the signals are not orthogonal, certainly you see the previous equation which we used is absolutely valid. So, the approximation of the signal can be given by the equation in the combination as we discussed in the first equation part, which is the inadequate. So, to further reduce the error, we can rather incorporate another signal C of t with the proportionality constant g, and we can write you see that this gamma rather. So, A of t is almost equal to beta into bt plus gamma of Ct, just to properly fit that part. So, you see here the error can be now straightway taken as A of t, earlier it was A of t minus beta times of B of t, now further we need to add minus gamma times of C of t, and then we can find out the mean squared error. So, mean error in that squared form is nothing but 1 by t integration 0 to t into this all A of t minus beta times B of t minus gamma times C of t whole square into dt. and we can go with the same procedure when we are trying to minimize this. So, we have the error differentiation of the error with respect to d beta is nothing but equals to see the this 1 by t integration of 0 to t to beta b square t plus gamma times of beta t theta t minus 8 a of t and b of t into dt equals to 0. So, now you see here we have the two main parameters b of t and c of t can be chosen like which are mutually orthogonal, and the second term of the like this feature above term can be straightway taken away, this beta t and theta t. So, when we are doing this, we have the beta is nothing but equals to this integration 0 to t a t b t dt divided by 0 to t beta b square t into dt. That means you see here we have the same equation which we derived when the c of t was not added. And if we minimize this error, again we have the same thing. So, we can say that like we can like solve this equation for gamma part. So, we can have the gamma is nothing but equals to 0 to t a of t c of t divided by you see 0 to t c square t dt. And when we are comparing these things, now we can say that the approximation function this a of t into c like gamma times of c of t can be straightway improved, and if we want to improve those things we need to add the another orthogonal signal, and we can simply minimize the mean squared error versus you see a t which is independently on any other signal part. So, that is very simple that you see like we can straightway put the orthogonals signal of the sine n omega 0 t and cos n omega 0 t, and then you see here we can do that. So, since we know that the sine and cos are orthogonal for all the integral value of the n, the sine n omega t and we can say cos n omega 0 t. So, for the time integral t which is nothing but equals to 2 p by omega 0, we can simply see that how the orthogonal property to decompose a periodic signal into sine and cosine component and can be straightway used. So, if we want to go for the desired decomposition of the signal into frequency component, say my frequency fn is nothing but equals to n by t, then straightway we can simply decompose the Fourier series with respect to again the same the a of t which is you see my main signal with the periodic feature, and if I just want to approximate these in terms of the sine and cosine, now I have this a of t is nothing but equals to beta 0, the beta 0 the initial part at the like basic, and then you see the expansion plus summation of n equals to 1 to infinite beta n cos n omega 0 t plus summation of 1 to infinite you see gamma 0 sine n omega 0 into t. So, this is you see the perfect representation of the Fourier series decomposition of the signal a of t, and the beta like these beta and gamma can be straightway calculated using these equations, where the beta 0 is nothing but equals to like like minus t by 2 to t by 2 the entire signal, in which you see we have the at dt divided by minus t by 2 to capital T by t, this one minus t by 2 to t by 2 this like L square over dt, or we can say that when we are just go for this one we have 1 by t integration of minus t by 2 to t by 2 a of t into dt, where you see like these beta n and gamma n can be straightway calculated using this cos and sine parameter a t cos omega t n omega 0 t dt sine n omega 0 t dt. When we are doing these things we can get straightway 2 by t of these parameters. The interval of the integrations in all the in all these above you see integration is minus t by 2 to t by 2, but could be like just well as you see 0 to t, because you see we know that when it is being varied from minus t by 2 to t by 2, we can assume that you see this variation is of the periodic form, and we can consume all the information for describing these coefficients. And it is also shown that the corresponding sine and cos terms can be combined into single this one by adopting you see like a constant phase angle, say phi n. So, we have a of t is nothing but equals to beta 0 plus summation of n equals to 1 to infinite, that we are doing delta n into cos n 0 omega t minus phi n, where delta is the amplitude which can be immediately computed with the composition of both the signals square root of beta square plus gamma square, and phi n is nothing but the phase angle which can be calculated as tan inverse of gamma n divided by beta n plus m pi. So you see, like the delta, which is the basic term here, which we have used here, is nothing but the signal's amplitude for the first tone, or we can say this is what my amplitude of the fundamental tone. Delta 2 can be also be used, you see, where you see like the second tone, or delta 3 is the signal amplitude for the third tone, or we can see, you see, like the fundamental tone for delta 1, the first derivative, in which we are saying that the first overtone is delta 2 and second overtone is delta 3 is there, which is absolutely showing the third tone is there. So in order to like to calculate, you see, the each frequency component as the complex, or we can say rotating vector, we need to see that what is the resultant feature of the simpler computations and how we can get, you see, the Fourier series out of it. So sometimes when you are trying to describe these Fourier series in the sinusoidal feature, we have, you see, very common part, A of t is nothing but equals to all the summation of these, like the sinusoids in terms of delta n e to the power iota n omega 0 t, where omega 0 is the natural frequency of the system, and we can make, you see, like the system coefficient, say dn is there, then we can say the delta n is nothing but equals to the minus t by 2 to t by 2 a t e to the power minus iota n omega 0 t into dt divided by this minus t by 2 to t by 2 1 square dt, or else we have this one. So when we are trying to compute delta n, we know that we need to have a of t, the amplitude of the signal, and there you see exponential features e to the power iota this omega n, this n omega 0 t into dt. This is what my exponential decay is there of the entire, you see, like the sinusoids are. So in this, the negative frequency are simply showing that, you see, like that we have the real quantity which can be described with the aid of two oppositively we can say rotating complex vectors, and each of which is clearly showing the complex conjugate of each other. So we can say that the Fourier series is converges to the function which is equal, we can say, like to the original function at point of continuity, or we can say to the average to two limits of discontinuities. In between that, we can say f bar is nothing but equals to, if it is, you see, here we are in terms of minus pi to pi, then we can use, you see, the limit of f, this is a linear summation, and if you are saying that no, it is, you see, in like x0 is minus pi, then we can straightway go for what the additional features are there in that. So this is what, you see, the approximations are. When you know that, you see, we have the squared, you see, like this main information, then you see here we are trying to make, you see, like this curve fitting. So this is, you see, this with the single sinusoid, that's, you see, lots of errors are there in that. So now then we are adding 2, in that, you see, here we are almost try to approximate, minimize the error in that. But again we know that, you see, lots of, you see, these like these blocks are there which are being left out. Then we are going for more number of nodes at the individual component. So we have, you see, the 3 featured at this. So you can see that now we are almost in the close proximity of the actual a of t, this whatever the signal is, and when we are going for the number of n is becomes more there now, you see. So then you see, like you can see that this is absolutely, you see, what the required, like the signal strength is there, and how we are, like decomposing this part. Now we are using, like one of the numerical in which we have a rectangular wave, and this rectangular wave is clearly showing with, like a of t with the time. Now you can see that at this point the total amplitude variation is a to minus a, and you see here this total period right from 0 to t by 2. So in between t by 4, 3 t by 4, minus t by 4 and minus 3 t by 4 is there. So this is, you see, the square wave which is simply varying in that particular time period and the amplitude part. Now we would like to calculate the coefficients there for this rectangular wave. So we have the beta 0. So as we discussed already, the beta 0, which is nothing but equals to 1 by t integration of minus t by 2 to plus t by 2 was there. Now here we need to go up to minus t by 2 to first 0, in which you see here minus a is there. If you look at this, it is supposed to start from minus t by 2 to, you see, like this is what it is what it is there, to, you see, like when we are going up to 0, we have the minus a. So minus a into dt plus 1 by t, 0 to t by 2 means the upper side a into dt. So when we are now trying to do this integration feature, we have minus a by t into d into whatever the t function is there, it is you see minus t by 2 to 0 first, and second is also plus a by t, for which you see we can simply apply this 0 to t by 2. So when we are doing this, our beta 0 is 0. That means you see the time average value of the signal, which is obviously you see it is a squared value. So time average value is equals to 0. So then we can go with the beta n, and beta n is nothing but equals to minus 2 2 by t integration of minus t by 2 to 0 minus a cos n omega 0 t into dt plus 2 by t. Now 0 to t by 2 integration a cos n omega 0 and t into dt, and when we are now making equal to this, so now we have the minus a divided by you see the n pi into sin n pi plus a by n pi sin of n pi. So you see here again it is the beta 0 which is even making on that is also 0. So when we are now going to the like the additive this part gamma n, the gamma n is nothing but equals to 2 by t minus t by 2 to 0, again same minus a sin omega n 0 t dt plus 2 by t integral 0 to t by 2 a sin n omega 0 t into dt. And when we are making this now, we have the gamma is nothing but equals to see the two main value. When you see we have the number of odd waves 1, 3, 5 and all, we have a clear amplitude 4a by n pi, and when we are using the odd terms 0 to 4, sorry the even terms, sorry 0 to 4 it is 0, and when we have the odd terms it was 4a by n pi. So like when we are decomposing this now, it is very clear that it only consisting the odd sine wave. So you see here when we are trying to now make the Fourier series through this decomposition, we have a of t is nothing but equals to the amplitude 4a by pi into sine of omega 0 n is now 1. So omega 0 t plus 1/3 of sine 3 omega 0 t plus 1/5 of sine like 5 omega 0 t. So that means you see here the odd terms are clearly showing their presence, and the only sine component which appeared in the Fourier series is because of the rectangular wave is an odd function, and odd functions can be decomposed into sine components since the sine function is like itself is odd. So you can see that this is what the clear expression of the basics of these Fourier series is as. So by definition we can say that a function is odd if it has the property a of minus x is minus a of x. That is what you see we already like done in our basics, that if we are talking about the odd property, certainly you see here the dependency of a of any function minus x is certainly be this one, and even if it is if it has the property of this a of minus x equals to a of x, then also we can say that you see here like these things are being clearly termed out. So if the rectangular wave is shifted to t by 4 to the left, making it symmetric about the t equals to 0, it becomes an even function instead and can be built up exclusively for cosine term. So you see this is what you see like a clear representation is there of the sine and cosine with the like relation of the t by 2 to t by 4. So the raw analog signal is typically brought into the portable digital instrument and process it for like this variety of the user functions, and depending on the frequency of the interest, the signal may be conditioned through the series of these high pass and low pass filters. That is what we discussed. And then you see here in this decomposition we need to check it out that what is the time frame in which you see here both the components sine and cosine can be included, and what the orthogonality conditions are there when we are doing the decomposition of the Fourier series. So in this lecture you see we simply like decomposes whatever the time domain informations are there which we are measuring using all these transducers, whether it is you see like in terms of the displacement, velocity and acceleration, and then we will try to convert this into Fourier series. And as I told you, one of the unique feature in that, if it is like the stationary wave terms are there in which you see a clear waveform it is in the like form of we can say the periodic wave, simple harmonic wave, it can be easily decomposed because it can be divided into sinusoidal and cosine feature and the orthogonal feature, and that can be added according to the Fourier series component, the sinusoids. But if it is, you see, the non-stationary part is there, then we need to take that, you see, what is the nature of this non-stationary feature of the signal, where the abrupt, you say, if bump is coming or any abrupt changes are there in that. So, if that can be analyzed using the short term Fourier transformation STFT, like Hilbert-Hung, or even we can go for the wavelet transformation by taking the small part and analyze for the non-stationary part there itself, using some statistical features of this entire wave part, which where it is being like the non-stationary in the nature. So, in this lecture that all the information was discussed. In the next lecture now we are going to discuss about the filters, because you see when we are talking about, you see, the signal processing, the filter part is very important, that you see here how we can adopt the low pass, band pass, or you see octave band, or means like various types of filters, because this is also one of the important part prior to go for signal processing, how we can adopt those filters, how we can design those filters there itself. Thank you.